Essentially what I want to do is I want to compare the relative strengths of Kas and Kbs. So I'm going to give this a shot. Relative strengths of Kas and Kbs. All right? And I've essentially got two scales that are supposed to be like a pH scale, but they're not a pH scale. On the top scale, I'm going to write Ka values, which means I'm going to be dealing with acids. And on the bottom scale, I'm going to be putting Kb values, which means I'm going to be dealing with bases. Whether they're conjugate bases or whether they're just regular bases, it doesn't make any difference. I'm going to slide this up just a little bit. That title said relative strengths of Kas and Kbs. Now, when I do this on my paper here, and this is the way I've done this in the past, I use a nice ruler because I want, again, 14 units, just like our pH scale, except I'm not going to be putting them in whole numbers. I want here in the middle, where's the black pen? 10 to the negative 7, right? In other words, I'm not putting a power number. I'm not taking the power out of it. I'm just putting the actual value of the Kas. Over here, I'm going to put here 10 to the 0, just like I would if it was kind of like a pH scale, but it's not. And up here, I'm going to put 10 to the negative 14. And I'm going to do the exact same thing down here on the Kb scale. 10 to the negative 7, 10 to the 0, and 10 to the negative 14. Okay? All right? And all I simply want to do is plot on there some acids and their conjugate base, and perhaps a base and its conjugate acid, so that we can talk about their strengths. Now, before I continue, if I'm way down here to 10 to the negative 14, what's the strength of the acid going to be if the Ka value is way over here at 10 to the negative 14? How would you describe that particular acid if it has a K of 10 to the negative 14, Jess? Weak, not just weak, but let's call it super weak. Like, I mean so weak the H's are hardly going to fall off. Does that make sense? So way down here, we're going to have our super weak. Okay? And if I have an acid that has a K of 10 to the 0 or 10 to the 1 or 10 to the 6, how would we describe the acids over here? Strong, right? These would be strong. I don't really need to put super strong. Maybe I will, just because super like is a neat word. Super strong. All right? They're strong. They're all going to fall off there. Now, in the middle here, I've got this 10 to the minus 7. We've been calling them weak acids and weak bases. But to just kind of differentiate between the super weak, where an H hardly ever falls off, I'm going to put here in the middle moderately weak. All right? So it's like moderately weak. It's kind of weak. It's weak where we can use the shortcut, but it will still change the pH. These super weak guys, we can use the shortcut, but it really doesn't really change the pH because hardly any H's fall off. Does that make sense? Okay. So let's get some data here. Could somebody find me the Ka for acetic acid? Ka for acetic acid. I want to plot it on my Ka graph. What do you got there, Shauna? So negative 5. If this is 0, then I'm going like 1, 2, 3, 4, 5, 6, 7. I want to put it right in here. Oops, and I don't want yellow. I want black. I want to put it right in here. And could you tell me the number again? 1 point. So I'm going to put here 1.8 times 10 to the negative 5. And this is acetic acid, CH3COOH. And if we use our Ka-Kb relationship, we could figure out the Kb of the acetate ion, and it's going to be that they multiply to 10 to the negative 14, which means I'm going to have about a 10 to the negative 10 or negative 9. What is the number for acetate right beside it? Christian, what do you got? Now I'm on the KB scale, but I'm now 10 to the negative 10, so that's 8, 9, 10, and in reality, I will be exactly the same distance from that negative 7 as I was on the Ka, because that Ka-Kb relationship will always multiply to negative 14, so you automatically flip down to the opposite side. It automatically happens mathematically. So what was the number again, Christian? I was getting the negative part, but negative 10, and that's CH3COO minus. And just to visually represent it, I like to take a ruler. You guys use a ruler, but I'm going to just use a line. When you have a Ka and you find its Kb, it will always cut across that 10 to the negative 7 and will go on the opposite side of 10 to the negative 7. So what happens then? Here then we have a moderately weak acid, and when it loses its H, it becomes a moderately weak base, but it's a little weaker than what the acid was. Does that make sense to everybody? I got a moderately weak acid, slightly stronger than the middle, and when it loses its H, it becomes a base that is still moderately weak, but it is weaker than what the acid was. Acetic acid and its acetate is better at being an acid than it is at being a base. All right? If this is confusing, I'm going to keep talking. We can laugh at the book on the ground. That's great. Let's take a look at now a base. Somebody find me the Kb for NH3, ammonia. What do we got? Yep. Handily, it's the same as the Ka for acetic acid. 1.8 times 10 to the negative 5. That's for NH3. So NH3 is a moderately weak base. It's slightly stronger than that midpoint. So if we then take a look at the Ka of its conjugate acid, because it's the same value, I'm going to have the same on the other side because of that relationship. 5.6 times 10 to the negative 10. And again, that's for NH4 plus. And again, just to visually represent it, we cut across the middle, and our moderately weak base, which is a little bit on the stronger side, becomes an even weaker acid. But still, it's a moderately weak acid that has acidic ability. Okay? Let's now take a look at something like acetic acid. What's the Ka for a strong acid? Sorry, not acetic acid, hydrochloric acid. What's the Ka for a strong acid like hydrochloric acid? What do you got there, Jenna? 1 times 10 to the 6th. That puts me like way out here, right? So I'm going to just put out here 1 times 10 to the 6th HCl, and that is a super strong acid. What's the Kb for Cl minus? We never really think of chloride as being a base. But what's the value? Yep. So where does that put me? Way out here on the back side here. It actually would put me equal distance out this way. Way out the back side. 1.0 times 10 to the negative, don't have enough room here, negative 20. Negative 20. That's for the Cl minus. Cl minus. How would you describe HCl? How would you describe that? Super strong. If we were to look at chloride just in water, Cl minus, how would you describe that as a base? Super weak. It's so weak it does nothing. Super weak bases sit around in the water and they don't even play the game worth 2 cents. They're terrible at it. We actually have another term for ions that don't want to play the game. Ions that just kind of stand there. All right, chloride, you're in the water. Come on, you can play. You're a base. You're a super weak base, but you could play. No, I don't want to play. What do we call those ions that don't do anything? They come to the party, but they don't play the game. Yep. Observational ions. Yes, observational ions. No, spectator ions. These guys down here are spectators. They're spectator ions. The chloride ion in water technically is a super weak base, but it's so weak it doesn't do anything. It doesn't play the game. Let's take a look finally at a base equivalent. Now, on that table, there is no strong bases. So let's just pick one. We know a strong base. NaOH is a strong base. I have no idea what the Kb value is, but let's say it's really big. Good enough. It's going to be a huge number. All the OHs fall off, which means we can think of when the OH falls off, the Na, we can think of the Na plus as if it's some kind of a conjugate acid. And it technically is. Where would it be? Way out here. So if I then had Na plus as a conjugate acid, what would the size of its Ka value be? Yep. Very small. Super small. And we already know this. Sodium in the water, which is technically the conjugate base of a the conjugate acid of a super strong base, they're going to go overtime, folks. I guarantee it in that assembly. So I'm going to finish this off. So I know you're getting a little excited, but I'm guaranteed they're going to go a little overtime. So Na plus, I want you now to think of Na plus as if it came from from NaOH, which is a super strong base. That automatically makes Na a super weak conjugate acid. And if it's super weak, what do we call it? It's not doing anything. It's not playing the game. Yep. It's a spectator as well. Spectator. All right? And again, just to finish off this illustration, going from that super strong, it cuts all the way across to become super weak. It's conjugate, whatever it is. And same thing here with the base. It goes from super strong to becoming super weak. And if I did my picture properly, all of these things should be crossing in the middle because of that relationship between Ka and Kb. Because tomorrow we're going to have to critically be looking at ions, and we're going to have to ask ourselves the question, what is this thing going to behave as? Is it going to behave as a moderately weak acid or a moderately weak base? Or is the ion going to behave as like a super weak acid, a spectator, or a super weak base? We won't be dealing with the super strong guys. That was just to illustrate the ions. And that hopefully helps you, guide you into answering the questions. What's in the water? Is it an acid in the water? Is there a base in the water? Do I have to use an acid equation or a base equation? Because that's what it's going to come down to. Okay, minimize that. So, we don't need to write this down. We're going to answer this in a moment. When salts dissolve in water, they dissociate into individual ions, and they may or may not exchange an H+ in a Bronsted-Lowry acid-base reaction. Therefore, they can affect the pH of a solution. NaCl is neutral, sodium carbonate is basic, ammonium chloride is acidic, and we'll explain that right now. So let's write down hydrolysis to begin with. We have been using this equation We were introduced to it last week. When I introduced to you the concept of weak acids and weak bases, and Bronsted-Lowry acids and Bronsted-Lowry bases, I talked to you about a reaction that happens between the weak acid in water and the weak base in water. But I didn't give it a name. I just called it a Bronsted-Lowry acid-base reaction. There is a technical name for this little reaction, and it's called hydrolysis. Hydrolysis simply means the breaking apart of water, and that breaking apart of water is the reaction that takes place with our weak acid or our weak base. So nothing new on that slide. What's that? Besides the definition hydrolysis that defines that little reaction. Okay? And it can be done by a moderately weak acid or a moderately weak base. Okay? Again, let's not write right away. I just want to take a look at the slides. Salts that form neutral solutions. Yeah, you can write this down. And I'm actually going to do the examples here with you. Cations of a strong base. We've already encountered those in my little crisscross diagrams. The cations in a strong base are what we call spectators. Group 1 or 2 cations. Some examples, Na+, K+, etc., etc. Those are all spectators. Anions of strong acids. We already encountered those as well. I've already taught you that those guys also make spectators, right? If they're from strong acids, these are also spectators. They do nothing. Why? Because they came from a strong acid. I always want you to think, when you encounter ions, think about where they came from. And what I mean by that is, what acid or base did they come from? That's what we're really doing here. We're taking the salt, and we're going to break it apart, and we're going to say, where did you guys come from? What acid and what kind of base did you come from? And then we'll make the logical statements needed to answer the question. So my example is going to be here, NaCl. Okay? Now when you get a salt, if I ask you, could you tell me if it's going to be acidic, basic, or neutral? The first thing you have to do, all right, number one, is do a dissociation reaction. I'm going to spell dissociation wrong, so I'm just going to put this. Remember, dissociation reactions are simply breaking the ions apart. NaCl aqueous is going to produce Na plus Cl minus. All right? So break the ions apart. Dissociation is completely different than hydrolysis. Dissociation is just the ions falling apart. Hydrolysis is, does it react with water? Do the ions react with water? So now that you've got your ions, let's take a look at each of those ions. Na plus. Exactly. It's a spectator. I just want to just put a little more information here. This is the super weak conjugate acid because it came from a base. Yeah, remember it cut across? It's a super weak conjugate acid. Therefore, it's a spectator. Nothing. If it's a spectator, therefore, no hydrolysis. And if you can't spell, you have to say it that way. Hydrolysis. And that's a Y. Yeah, that's the ugliest hydrolysis that you've ever seen. But I'm not fixing it because I'm recording. Does it make sense, though? Sodium came from sodium hydroxide. Sodium is a super weak conjugate something, and it is not going to react with the water whatsoever. Cl minus. How would we describe it if I wanted to write a statement like this? How would I describe Cl minus? Super weak conjugate base, spectator, no hydrolysis. Does that make sense? Super weak means they're not going to react with the water whatsoever. Super weak conjugate base, therefore spectator, therefore no hydrolysis. If there's no hydrolysis whatsoever, then there's no OHs or no H3O pluses formed. It's neutral. Therefore neutral. Okay? Now let's analyze some other acids and bases or other salts that have some moderately weak guys in it. That's essentially what we're doing. Okay. Yep, ignore that writing underneath there. Salts, yep. What are we going back here for? What are we doing? Really? Oh. This pause is for Anthony McCreary. It's going on the internet, by the way. Okay. Yeah, go ahead and write that. And I'm going to cheat and look at my example here because I want to write the example down. Oh, come on. My example's on the next page. Just write that, and then I will make up an example. Sounds like fun. So the example I'm going to do here is ammonium chloride. All right? I've already said the first thing you have to do is dissociate it. I'm not going to rewrite the dissociation. Let's just go straight from here. So let's say we have some ammonium chloride aqueous. We're going to dissociate that. NH4 plus Cl minus. Let's analyze now our ions, and I'm going to actually start with the Cl minus, all right? Cl minus, well, we've already encountered this guy. Comes from HCl. HCl is strong, so Cl is super weak. Super weak. And I don't even care if it's a conjugate acid or a base at this point. If it's super weak, it's doing nothing. So I can actually shorten this up. Therefore, what is it? Spectator. And therefore, how is it going to interact with water? It isn't. No hydrolysis. Now we analyze the other ion, NH4 plus. Well, where does NH4 plus come from? Comes from NH3. And if we check our sheet, they're kind of moderate. They're in the middle. So that means this is a moderate conjugate what? Now this is the hardest part. Is this an acid or a base? It's an acid. It's a conjugate acid. It's a moderate conjugate acid. Therefore, it's not a spectator. Yes, hydrolysis. And I'm going to just quickly write the hydrolysis reaction. NH4 plus water. It is an equilibrium. What am I going to get? An NH3. And here's the important part. I get the H3O plus. I get an H3O plus, which means right from here, what am I going to say about this particular solution? It's acidic. It's going to make it slightly acidic. Therefore, acidic. And that's what it's all about right there. Which means if I had given you a concentration, let's say 0.02 molar, I would use the acid equation to figure out what the pH is. Because I would have this hydrolysis, and therefore I would simply stick it in the acid equation, the weak acid equation, and I'd get its pH. We'll do that quickly at the end. Hopefully we got enough time. Okay? All right. Let's move on. Okay, ignore all this extra. Oh. How's it going back there? We're good? All right. We did that example. Let's talk about these guys here. And let's just, right there. And the example that I will do here is KNO2, not KNO3, right? Because nitrate is one of those that comes from a, what's that? Oh, because it's different than the, no, I changed it up. I knew that it wasn't one that was. What did I use, HF before? Sorry, KCN? Oh, that's no fun. Let's do KNO3. Oh, goodness gracious. Just scribble it out. You know you want to. Just scribble it. Like, just with pen. Just scribble. I didn't actually change it to cause you discomfort, but that is a little bonus on the side. It's kind of entertaining. So, if you're given a salt, right, dissociate it. Don't even, you know, if I'm asking, is it going to produce an acid or a base or be neutral? Dissociate it. So that's aqueous. That's going to produce a K plus and an NO2 minus. It doesn't matter the order, but I'm drawn to the K plus, because where did the K come from if it was an acid or a base? The K is going to come from KOH, right? We have to be thinking that way. The K, the only way it can be an acid or a base is to come from KOH. KOH is one of those ionic ones that dissolve like crazy, so that's strong. So what is K? What is K? Super weak conjugate acid. Spectator, no hydrolysis. Super weak conjugate acid. Spectator, no hydrolysis. NO2 minus. You could confuse this with an NO3. You could be forgetting about your list of weak acids and strong acids and, oh my goodness, so many things. Go to this piece of paper. You could even forget about whether we're dealing with a conjugate, blah, 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 blah. Go to the piece of paper and find NO2 minus and tell me what side it's on. Is it on the acid side or is it on the base side? Here I'm really breaking it down, the simplest of simple. You're doing this problem, you forget all this crisscross thing, you get an NO2 and you go, oh my goodness, what is this behaving at? You find it, and which side did you find it on? The base side. And what's the power of 10 of its KB? 10 to the negative, that's moderately weak, right? It's in that middle. That's a moderately weak base. Whether it's a conjugate or not, I really don't care. It did come from nitrous acid, right? But who cares? If you're writing the test and you're kind of struggling, you find that, and you're going to find that that's a moderately weak base. Whether you put conjugate in there or not, I don't care. It's a true statement. So if you know where your moderately comes in with a power of 10, you're doing just fine. Therefore, yes, hydrolysis. As soon as you say it's moderately weak, right, you've got hydrolysis, NO2 minus plus H2O. Let's complete this. Because it's behaving as a base, what am I getting as products here? Jason? NO3 plus NO3 plus, think it through. What did you do there? You did something goofy. HNO2, that's a Monday morning gap right there. Well, that's coming off of the NH3. That's okay. HNO2 plus OH minus, and therefore, this is going to be what? Basic. Oops, that's arrows in a terrible spot. Basic. All right? Because we end up with that. Yeah, it says basic. All right? Okay? Let's do a couple more. We're going to go? Yeah, we don't care about that writing. Don't care about that example. You can write that down. To where? I'm hoping you can.
Okay, go ahead.
No, I'm going to help you.
No, I'm fine.
I want to change my example again. All right, you're right, we won't. Am I doing NH4CN? All right, I'll do NH4CN. So let's say I've got something like NH4CN. Same thing, break it apart into its ions. So let's dissociate it. NH4 plus CN minus. Ammonium cyanide is what that is. Well, let's analyze each of the ions just as we did before. NH4 plus. Again, let's say that we're overwhelmed. We don't know where it's coming from anymore. We don't know whether they're acids or bases. We don't know what we're thinking. We're going to this page. You're finding NH4 plus and you're telling me what side it's on and what it's going to behave as. Yeah, Albert? And how would you describe it? Strong, moderately weak, blah, blah, blah. Moderately weak. So we're going with a mod, weak, acid, and therefore, yes, hydrolysis. And let's quickly write the hydrolysis. I'm going to try to squeeze this in because I want to get both of them on the page. So that means NH4 plus H2O is going to get me NH3 plus H3O plus. And I would like the Ka to that, if someone could tell me that, if it's nearby. 1.6? 5.6? 5.6 times 10 to the negative 10. All right? And you might say, hey, it's going to be acidic. Well, hold on. We got to take a look at the CN this time. CN minus. Again, we're overwhelmed, too much stuff. Go to the page. What side is it on? What's it behaving as? It's a base, right? And I'm thinking it's a moderately weak base. It's hanging around 10 to the, well, what is the number? That's still a stronger base, but it's still not, you know what I mean, in the strong region. We're still calling that moderately weak. 10 to the 0 or 10 to the 1 when it's not a negative. Yep. Moderately weak base. Therefore, yes, hydrolysis. Let's write the hydrolysis reaction. Cn minus plus H2O. What's it going to be? This is really conjugate acid base swapping, right? We're really reviewing our conjugate acid base stuff. HCN plus OH minus. Jason picks it out of the fire from that first gas. That's okay. And what's the KB? We had 10 to the negative 5. I just need the front numbers. 2.0. 2.0 times 10 to the negative 5. All right. What do we have here? Is it going to present itself as being acidic, or is it going to present itself as being basic? What do you think? What do you think? It's obvious. Just look at the numbers. It comes from the numbers. Yeah, basic. Why? Because the Kb is bigger than the Ka, and which means cyanide is better at being a base than NH4 is at being an acid, so it dominates. It's going to be acidic. Now, that calculation is difficult to do, and I won't make you do a calculation like that because you've got two equilibrium happening at the same time. But we can qualitatively say, because the Kb is greater than the Ka, therefore, it's going to be a basic solution. Okay? Make sense? So that's if we don't have spectators in there and we've got a couple of moderately weak acid and moderately weak bases. All right, that's that. That's not a big deal. Yeah, we've already wrote that down. Predict whether that's going to be acid-base neutral, determine the pH. I do want to do this example here, you bet. So let's work through this one. This just has an add-on. What would the pH be? So all we've got to do is determine whether it's going to be a moderately weak acid or moderately weak base, and then just apply the appropriate equation. And on a test, this is the way I present this type of question. I make you think through how it's going to behave, and then we do the calculation. Dissociate it first. Take a look at the ions. Spectator, not a spectator. You can write out the hydrolysis if it happens, so we can predict whether it's acidic or basic or neutral. Then we move on to the next question. You can go ahead, without me here, like you can finish it off. Na plus. What is it? It's a spectator. You know what? If you just want to write down spectator, that is spectator. If you want to spell it properly, spector. Spectre. That's funny. That's a bad guy in a James Bond movie at the beginning anyway. Spectator. All right. Anyway, if you just want to write that down, that's good. Good enough. All right? Done. No hydrolysis. I understand that. NH3. It's a spectator as well. Sorry. Hey. NO3. Spectator as well. It comes from HNO3, nitric acid, which is strong. Spectator. Therefore, what kind of a pH is it going to have if they're both spectators? 7. So neutral. Which makes part B a trick question. It doesn't matter how much of that stuff we have in it. What's the pH going to be? 7. Stop. Trick question. No calculation needed. Again, you don't have to write down all that conjugate, blah, blah, blah. When it's weak, I do want you to write down that it's moderately weak acid or a moderately weak base. I do want you to write that. But if you go straight to spectator, that's fine. This one won't be. If you want to just put number 2 and just put KNO2 this time, same question as number 1, it is. The exact same numbers. It's the exact same thing. It's just now I'm dealing with KNO2. So the numbers are the same. What's K plus? How is it going to behave in the water? Spectator comes from KOH. NO2. Again, if you're not sure where it comes from, yeah, it's a base. It's a moderately weak base. Yes. Hydrolysis. NO2 minus plus H2O. And I'm just looking at the time, HNO2, so I'm going to just put down what we got, OH minus. Which means I'm going to use OH minus is equal to Kb times the concentration of that base, because it's a base. I just need, and I'm running out of space here, so I'll put it off the side, I need the concentration of NO2 minus. How much NO2 minus is going to be in that water? 0.10, because there's only one NO2 for each one of these KNO2s, right? So this is that classic break the ions apart. I could put 1 to 1, but I don't need to. 0.10 molar times 1 to 1, right? There's one NO2 in each one of these. So, root, whoa, that's a terrible root sign. What's the Kb for NO2? Somebody have it? 10 to the negative 11 times 0.10, take the square root, get the OH minus, take the negative log, get the POH, subtract from 14 and get the pH. This is where, don't clear your calculators, right? Just keep pounding through those answers. I'll take the POH. I don't even need that middle number. If you got the POH, that'd be great. Because in the end, I got to get pH. 5.8, that's the POH. POH, 5.8. One more decimal would have been nice, but it doesn't matter. And therefore, subtracting 14, what do you got? 8.2? 8.2. We predicted moderately weak base, and we're in the weak base territory. Fabulous. On the good old pH scale. Okay? So when you're given a salt, break it apart, analyze each ion, and then go ahead and solve for whatever it's behaving as, whether it's behaving as an acid or a base. And this one is going to be the other way. I'm not going to do that example. It's going to be a moderately weak whatever. There are some questions right there for you. And I've got one more little example, but I'll use it tomorrow as kind of a review. So we'll do that last little example as a little kind of summary and review for tomorrow. Sorry, I'm going to move that out of the way.